Hello ladies and gentlemen, welcome to Physics 20, Work Energy Power Lesson 7, Efficiency. Now, review. Mr. S is on top of the gym and he throws down a water balloon onto a student 12 meters down below with a velocity of 3 meters a second. What is the final velocity of the balloon? Now, we can do this as a V initial, V final acceleration displacement time question, or as we did last class, energy total, or mechanical energy, equals energy kinetic plus energy potential. So here we have to draw a couple pictures. So here's Mr. Sutton with the water balloon, and here's the poor schmuck I'm nailing in the head with it. So we have energy initial, which is energy kinetic initial plus energy potential initial. Now, just as I throw it down, so I have kinetic energy. And I have potential energy. And notice once again, it's initial. And as I drop it, it comes down and smacks somebody on the head. So I have energy final, which is energy kinetic final, plus energy potential final. Now the nice thing here is that my H final is 0, so my potential energy final is 0. So this is 1/2 mv final squared. Okay? So left side equals right side. Now, get lazy. What's the mass of the water balloon? I don't know, and I don't care because it cancels out. Now, right about now, some people go, oh, half and half. Why not multiply everything by 2 to keep the math simple? Okay, I can do that. So this becomes V initial squared plus 2GH initial equals V final squared. And I'm looking for the final velocity. Now I know V initial is 3 meters a second. So that's a second, that's a wretched square. 2 times minus 9.81 times 12 meters. Sorry, neatness freak, equals V final squared. Now, putting the math together, this is 9 plus, so V final squared is 244 meters squared per second squared, so velocity final is 15.6 meters a second, which is owie. Okay? Energy initial equals energy final, or energy is conserved. We don't need the mass, and notice we can multiply by 2 to make the math a little less nasty. Now, this energy is conserved leads into this last lesson, efficiency. Work Energy Power Lesson 7, efficiency. Now, efficiency. Some energy is always lost when you do work or transform energy. So, efficiency is energy out divided by energy in times 100%. Now we can rewrite that as power out divided by power in, because energy out divided by time is work out divided by time, and energy in divided by time is work in divided by time. Energy divided by time is power out divided by power in. Now, all you really have to remember is there's 3 different ways to write out the formula: energy, power, or work, depending on what I'm talking about. So, let's do a couple example questions I'll show you. A 13-watt fluorescent light bulb is 8% efficient. How much energy is turned into light every second? Now here I'm being a smidge confusing because this is power, which is energy per time or work per time. And how much energy is turned into, we're talking about energy every second. So 13 watts is 13 joules every 1 second. So every second we're talking about 13 joules. So efficiency now I'm going to do energy out, energy in times 100%. Now, energy out is what's useful. So, that's what's turned into light. In this instance, it's 8% of the energy becomes energy out, or light. Now we're putting in 13 joules every second times 100%. So multiply both sides by 13 joules and divide by 100%. The energy out becomes 1.04 joules. This is useful. Of the light. And the rest is lost to mostly heat or thermal friction. Now, that's basically it. Of course, a few tricks. Let me show you a couple. A 60-watt incandescent light bulb is 2% efficient. How much power is lost? Well, efficiency is power out. Oh, sorry, since we're dealing with power and watts, we're using the power version of this. It's all the same. Times 100%. So, 2% power out, 60 watts in. Now, this is part of the problem, is power out or power in. So this would be power in, 60 watts. Times 100%. Now when you do the math, power out is 1.2 watts, a useful energy, a useful power. The rest is lost. And we are asked to find how much is lost. So 60 watts minus 1.2 watts is 58.8 watts lost. Okay, so that's the first trick. It's not how much we use, it's how much we lose. Okay, so here's my favorite sneaky one. You're using a pulley system to lift a 100-kilogram engine block 3 meters up. If the pulley system is 94.3% efficient, what distance do you have to pull the rope when you apply a force of 520 newtons? You're going, what the heck? Well, your engine block, you're pulling up, there's your pulley, there's your rope, force applied. Okay, so think about this. You got force of gravity. You'll have tension in the rope, force applied. Okay, now, here we're dealing not with force, but with efficiency, work and energy and power. Now, what is work? Work is force times distance. So you have force, you apply force of 520 newtons, and the distance. So you have work, which is force times distance. And you have work done here. You have work done here, which is force of gravity times distance, which is mgh. Okay, so This is a 100 kilogram block. We're going against gravity, 9.81 meters per second squared, times a height of 3 meters. So the work you're doing against gravity is 2943 joules. Now, this is work out. That's how much energy you're getting out of the system, or how much work you're getting out, because some is lost. Now, efficiency, work out divided by work in. This is work in to the system. 94.3% equals 2943 joules. Joules divided by work in times 100%. Now, here I'm going to cheat and cross multiply. So work in 2943 joules divided by 94.3% times 100%. So work in, or win, is 3121 joules. Now, that equals force times distance. How far did you pull the rope? Don't know. But what force did you apply? So we're going with distance, we don't know. But distance would be work in divided by force, 3121 joules divided by 520 newtons. So the distance you pull the rope, 6 meters. Sorry, rounded that off too much. 3121 divided by 520, 6.0 meters. Okay. Now, see how that goes? Nothing particularly hard, but you got to work at it and you got to read the question carefully. So I'm going to pause the recording here because it's getting kind of long, and then we're going to come back and we're going to look at a couple more nasty questions. All right? Any questions, shoot me an email. Otherwise, good luck.